Good afternoon, everyone. Good morning. So this is the 2024 fall season of Landscapes Live, and today we are very happy to host Gareth Roberts, who's tuning in from London, from Imperial College London. And it will be the usual setup. So this chat will be locked for the moment. We will open it 5-10 minutes before the end of Gareth's presentation. You can write down your questions before the end if you have a burning question. And my co-host, Rita Carrasco, and myself will be reading through the questions and relaying them to Gareth. Before we start, a quick intro. For those of you who do not know Gareth Roberts, he hails initially from Durham, where he did his undergraduate work before going to Cambridge for a PhD with Nicky White that he finished in 2010. And then he slowly walked his way through Imperial College, starting in 2013 as a reader, and then become a lecturer, and now is a senior lecturer. And he comes back to us after a recovery year sabbatical in Southern California, where he worked at Caltech as a visiting associate professor, and this is going to be the core of what he will present to us today. A reminder that this is recorded. This will be posted on YouTube later, and you can see the different YouTube presentations of all of the Landscapes Live catalog on our webpage. Gareth, the floor is yours.
Many thanks, Luca and Risa and the Landscapes Live team for organising this. Much appreciated. I'm not quite a reader yet, so we go lecturer, senior lecturer, and then reader would be the next step for me. The unusual British system.
I got it in the wrong way around. My apologies.
To come, or at least I hope to come at some point. Anyway, so yeah, just as you say, so I'm going to talk mostly about work I did actually whilst I was in California last summer, and mainly with Omar Wani here. So you can see he's now at NYU. He was a postdoc in Mike Lamb's group. I'll talk it as a kind of jumping off point, the work that I did with Nicky in Cambridge, Nicky White in Cambridge, and since. And I'll be talking quite a bit, especially at the start of the talk, about work that came from two people who work with me, Geir and Victoria. Geir is in MIT now, and Victoria is in Potsdam. And what I really want to get at, let me just get rid of that. Oops. Hopefully you can see that. There we are. Yeah, what I'm trying to get at, and what's been bothering me for a while, is how we can try and understand how landscapes evolve across the scales of interest. And what I mean by that is from seconds to millions of years and meters to continents, which is a large number of orders of magnitude, 7 or so orders of magnitude. And I think for this audience, there's no real reason to have to explain why we might want to know why landscapes evolve. In general, we want to understand how landscapes acquire the geometries, the histories of acquiring those geometries. I come from a sort of geological background where we try to make use of information from landscapes to understand geologic processes. Mantle convection is one of the things I work on quite a lot. Tectonics, faulting, and so on is obviously a very big part of this community that we're in. We might want to understand how changes in landscape are related to changes in things like biodiversity and species richness, which is one of the things we work on. How climate and landscapes are related, and how we might pull out information about climate from landscape geometries. We and many others, of course, work on things like chemical fluxes, which are also quite intimately related to the geometry of landscapes, in particular how mixing occurs in landscapes and how that might change through time. And of course, there's a big resource and risk interest in understanding how landscapes evolve. As I say, I won't dwell on that for this community. So the problems as I see them, as up to where we're at now, is scale, stochasticity, so randomness, and unknown unknowns. So part of this stems from trying to understand scale-dependent geometries. So the physics or the phenomenology, the kind of kinematics that we have at some scale, knowing whether they're applicable at other scales is, I think, a really big problem for us, actually. And a lot of this talk is about how we might be able to address that. And this stems to things like changes in precipitation rate, changes in discharge, and in particular erodibility, which I think is really incredibly difficult to constrain with existing techniques. And just to give you a flavor for the kinds of scales that I'm thinking about in these problems, I'm going to lean on stuff that we've done for obvious reasons. But that's not to say there isn't a huge body of work out there from other people working on similar kinds of topics at these kinds of scales. But I'm just going to lean on a couple of our studies just to introduce the problem. So this is work that Victoria Fernandez worked on with me and various others during her PhD. And what we were interested in here, like we've been for many other continents, is how did North America, Central America acquire its topography? So we think it's related to the tectonic history. In particular, the topic that we're interested in here is trying to understand the history of mantle convection. And to get to that, we want to know the history of uplift. So one way we go about trying to do that is we can try and make use of some sort of geomorphic law to try and understand how landscapes acquire their form. And we make use of things like the stream power model that'll be very well known to this community. It kind of boils down to a very simple phenomenological kinematic thing, where really mostly what we're worried about is how fast slopes, so dz dx, slopes in topography, propagate. And there might be some set of rules that we have. So here we've gone for a very simple erosional rule where we've got some velocity prefactor, an upstream drainage area raised to a power of m, which is the kind of proxy for discharge. So the velocities decrease as we go headward as upstream area gets lower. We've some uplift rate, which might vary as a function of space and time. And that gives us some rate of change of elevation through time. Now that as it turns out, even ignoring lots of obvious complexities that exist, like changes in precipitation, planform changes, lithological contrasts, biota, that, as it turns out, has plenty enough complexity to fit most river profiles at these kinds of scales. So what you're looking at here is elevation, so from 0 to 3 kilometers as a function of distance, so 0 to 6,000 kilometers. This is for the Mississippi. So it's lots of tributaries of the Mississippi that Victoria mapped. So obviously the Mississippi's here. The observations are the gray, the little gray curves that you can see under here. And the theory, the best fitting theory for this particular type of inverse model that we're running is the dotted lines, which ends up with a pretty low residual misfit. And that generates an uplift rate history. This is the cumulative uplift history. So simply the integration of the uplift rate history that we solve for here. There's bits that we don't think work very well for sensible geological reasons. So these hashed out areas where there's a lot of transcurrent motion, so a lot of horizontal motion of plates. So we kind of don't really trust that patch so much. But you can show that these calculations, whoops, let me get rid of this. These calculations of cumulative uplift, they're consistent with spot measurements that we have from marine fossil assemblages. So Victoria's done a big job on pulling together those from the paleobiological database and other sources as well. So I won't dwell on this. I mean, you can look at the paper if you wish. But really, this is just to say that at these very big scales, as far as I'm concerned, you can get away with really quite simple understanding of geomorphic processes. Now, that definitely is not true at all scales. So I'm going to pull on another paper of ours. This is work that Gaia did with me when she was a PhD student. And she's been working on much more depth on a lot of these problems since. And this is work that Gaia did with Dylan Rood, a cosmogenic colleague at Imperial, and Victoria was on this as well, actually. And what we were very interested in here is trying to understand how Iceland acquires its topography, mainly for geological purposes, actually. So trying to understand the history of mantle convection. And that took us down the line of trying to understand how it acquires its topography. So we focused on one particular patch in here. I'm afraid my Icelandic pronunciation is horrendous, but I'll give it a go anyway. Jakobskia Afjolum, so through here. And this is a set of longitudinal profiles that Gaia pulled out of the ICE-DEM in this area. And we were really zooming into this change in slope, this nick zone through here, and in particular, this little patch through here, for reasons I'll explain in a minute. Just to get your eye in, this blue stuff here is the Vatnajökull glacier, so you kind of have to dial that out, mentally dial that out. And if we zoom into a smaller scale, so in here, this is where Dettifoss, apparently Europe's most powerful waterfall, sits. And you can see we're down at much smaller scales than what we've been talking about so far, down at orders of tens of meters, about 50-meter relief on this waterfall. And what we were very interested in here, what I was very interested in here is, could we recover information about how fast Dettifoss has retreated and try and get information that we might be able to parameterize a stream power model with, say, for instance. And what we did, what Geyer, Victoria, and Dylan did was collected a whole pile of cosmogenic dating from fluvial terraces along Dettifoss, downstream of Dettifoss and upstream as well. So you can just see Selfoss, the next waterfall upstream. You can just see it spray up here. And we were kind of filling in gaps in a way between what data that people like Edwin Baines and colleagues have collected a little bit before us. And that cosmogenic dating, again, I won't really go into the details. It's helium-3. We worried a lot about production rates, shielding, etc. You can read more of the details in Geyer's work. What that came out with was a retreat rate of order, kind of getting on to be about 1 meter per year. And it turned out that a very simple, if we zoom in again, a very simple bit of physics, block toppling. So kind of building on the work that people like Mike Lamb and Bill Dietrich and others have done on kind of relatively simple torque calculations, where they're very physics-based, there's body forces, surface forces, drag form, and so on. You could show, I think fairly convincingly, that the retreat rates here are essentially down to these blocks toppling about once per year to once per decade when discharge exceeds, gives you enough force to make these blocks topple. So that, in my view, is a pretty good explanation of what's setting the erosion rates in this area. But there's a problem, which is that if you go up to Selfoss up here, its retreat rate is about an order of magnitude slower than what you see in Dettifoss. And actually, it's got a pretty good explanation, I think, which is that the torque, the bending, the torque, the length of the arm is shorter because Selfoss is just a bit lower and the basaltic columns aren't as long. So it's fine physically, but in terms of stream power, what on earth do you pick? Do you pick this rate here, or do you pick this rate here, or are neither of them sensible? It stands to reason, I think, that at some point, Dettifoss may well overtake Selfoss upstream, which is moving much more slowly. Maybe it gobbles it up and makes a bigger waterfall. Maybe they dissipate. Maybe they do something else. So I think what this is saying is there's different physics at play at these small scales compared to what we might normally think is going on at much bigger scales. And I think for reasons I'm not going to get into here, but based on the spectral analysis of longitudinal river profiles, which is something we've worked on quite a bit over the last couple of years, I actually think there's a break in scaling from small scales such as these up to the big kind of continental length scales, which I think is telling us there's a change in physics, essentially. Importing observations from small scales to big scales and big scales to small scales is really something that should be done with extreme caution. So the challenges as I see them in fluvial geomorphology is that landscape evolution incorporates loads of different scale-dependent processes like those that I've just been talking about. We've a problem. Again, I know this is going to be very obvious to lots of people on this call, but erosion destroys information. So it's not like looking at stratigraphy and basin analysis, say, where you've got these nice records of subsidence histories on long time scales because the stratigraphy is sitting in the hole that you make. In this case, because we're often talking about uplifted topography, we're eroding the very signal that we might want to interrogate, which is just it's a problem we just have to deal with. Another challenge is that most approaches to modeling landscape evolution, I think it's fair to say this, are phenomenological. So like stream power modeling, the kinematic. And quite often they come with, in my view, pretty questionable assumptions. So, I don't doubt you could see 100 papers this year that make an assumption of steady state. And I think that's a really hard assumption to defend, actually. Or we make assumptions about arbitrary uplift histories. So chi analysis is one example where this is manifest in where we put the lower bound on the integral. Like we don't often know where these erosional signals are propagating from. We might make some decision about how that is, and we might think it's reasonable, but actually our information on that's really pretty limited, in my view. Independent observations to constrain it are really pretty limited. A general challenge to doing it the other way, so to go from a kind of first principle sort of physics-based approach, is that we tend to be forced to focus on small spatio-temporal scales where experiments are repeatable or we have enough information to constrain our physics-based modeling at small scales. So we know discharge. Obviously, as you get to longer and longer timescales, geological timescales, that information is very, very uncertain. So a consequence of all this, I think, is that we've very little understanding of whether extrapolation of observations or theories is reasonable. So I don't really buy into the view that if we understand how every little bit of a river works or erodes on a small scale, we can somehow stitch that together to understand the big scales. I don't really think it works like that. Certainly not with the deterministic sort of standard deterministic approaches. I think we have to do something else to do that, which is what I'm going to talk about here. So in short, in my view, and this is very much my view, and I'm not speaking for the other people whose names I put on the front of this talk for sure. They might agree with this, but they might not. In my view, there is a lack of existing theory that can incorporate the physics across the scales of interest. So I don't think there is a general theory of landscape evolution, but it'd be very desirable to have one. So the way I've been thinking about addressing that issue is about answering this question. So how do we incorporate not knowing things into a theory of landscape evolution that embraces scale? So coming at this from a sort of geological point of view, there's no way we can know discharge on a Tuesday 30 million years ago, and we never will know that, I don't think. But that's not to say we might not know the distributions or the kind of functional form, perhaps, or the stochasticity of rainfall that we could apply into these schemes. So what I've been trying to do is build that into a kind of theory of fluvial erosion that has stochasticity at its core. And this is a bit different, I think, to what typically happens with building stochasticity into the stream power model through randomizing discharge. It's a change in approach, as you'll see. So what I'll talk about are kind of 5 approaches I've been taking to tackle this issue. So one is incorporating randomness into predictions of erosional front migration. So we could think about that as waterfalls or knickpoints or knick zones propagating, using kind of established mathematics from various bits of physics, mathematical finance, and so on. So these Langevin type equations and Fokker-Planck. I'll then talk about things. There's kind of limits to what I think we can do with those equations actually for Earth surface science problems. I'll talk about how we can do alternative things with sort of first principles approaches to developing stochastic theory of landscape evolution. And part of this comes down to treating landscape evolution as a Markovian, so memoryless probabilistic problem. I'll talk about how I think this is amazing still, these very nice analytical solutions that drop out for predicting landscape forms with stochastic driving and resisting forces. And the being analytical, it means we can avoid a lot of the challenges that we have when we're trying to solve stream power type models, certainly numerically. And I'll talk at the end about a kind of general algorithmic approach that gets landscape forms with no approximations, which I think is very useful properties I'll get to. So just to start with, I know perhaps probability kind of things are very well known to some parts of our community and less well known to others. So I hope you bear with me. I thought I'd do a kind of intro primer using what I'm calling, maybe a bit unfairly, but geological or geomorphic curiosities. So kind of things that might be a bit unusual, but look quite dramatic and quite exciting. So like waterfall migration, say. Like in the grand scheme of things, there's very little parts of rivers that have waterfalls on them, but they're very big dramatic features where often we can get information about erosional processes. So what I'm going to talk about here is how we can use kind of randomness stochasticity to understand how a waterfall or escarpment might retreat. Partly using this example from Iceland that I've already talked about, but it also partly stems from work that we've been doing over ages now. So the picture on the right of Madagascar it'll look very similar to chi maps for people who've been producing chi maps. It's basically just an integration of advective velocities upstream from the stream power model. It basically is chi, pretty much. And the idea here is that we're propagating some erosional front up to some headwater position. I won't dwell on this very much. The black squiggles through here are showing you where slopes are pretty high. So what this is kind of saying, what we sort of know is that there's an erosional escarpment in Madagascar up in these patches, which is probably, in my view, which we talk about in this paper quite a lot, generated by the regional history of uplift. But the point really here I'm trying to get at is that we often in geomorphic sciences, as lots of you will know here and work on here, is retreat rates of things upstream. So So what I typically have thought about when thinking about things like the stochastic, when thinking about things like the stream power model, is basically treating this in a deterministic way. So just as a very simple example, this might be some distance. So this y-axis here is distance, and the x-axis is time. And we might start with a waterfall up here, and it proceeds downstream at some rate. And in this case, we've just got a very simple deterministic model. And we do that, just a straight line, very simple. And then with some stochastic theory, it's very straightforward to put randomness in here. So just to get your eye, and that's the deterministic bit that we've already talked about. And we can weave in noise. And if we're careful or very picky about the type of noise that we weave in, we can get nice analytical solutions that drop out. So here, this is straight out of Gardner's book. So anyone who's worked on stochastic theory will probably have looked at Gardner's stochastic handbook textbook at some point. Here, we were assuming we've got a noise controlled by a normal distribution. And that means that you can then simply solve for position using some of these fairly standard bits of stochastic theory, where you can calculate the position at which these waterfalls propagate up, or our erosional fronts propagate upstream through time. So you can run this many times, kind of like an algorithmic way, and get some sort of distribution. And you end up with things that look like this. So if you do this is for 1,000 different solutions to the Langevin equation. The red here are the cosmogenic data. So there's a pretty big uncertainty on them, but they at least say that we can't have gigantic amounts of variance here. They probably bound the stochasticity that's permissible. So I'm showing you solutions that are kind of algorithmic here. And if you look at things like the distributions, they end up normally distributed, which is these little histograms. You could do something similar for Selfos as well, and you get a kind of similar story. Oops, let this person in. There we are. And you can, for lots of the problems that we work on, there's a pretty good view, a pretty reasonable view, I think, that erosional velocities would decrease upstream. And actually, that's pretty amenable to sort of analytical attack in these stochastic frameworks as well. So here, this dx dt, this retreat rate of a waterfall, you can now make that a function of position as well. Weave in noise again. You can solve a position again. You can implement that numerically again, algorithmically again. And you can also calculate expected values analytically. So again, I apologize if lots of this is well known to you. I think not for all of our community, this is so well known. The way to interpret this notation is the position of the waterfall given some initial position. So the little vertical line here is given. And these little angular brackets here are indicating expected values. So like an expected value x naught. So x naught's up here. It just ends up with this nice analytical solution, which looks like that. And you can calculate the variance analytically as well, which ends up giving you these lines through here. So the variance and twice the variance. So being analytical, of course, it means it's like mathematically perfect, which is very nice for us, I think. You can also solve this problem using Fokker-Planck mathematics. So I think most people who work on Langevin equations quickly end up looking at Fokker-Planck because they've got this intimate relationship. And the idea here is that we're calculating rates of change of probabilities. So for our problems, it might be the rate of change of probability of finding a waterfall in a specific location. That, for anyone who's worked on stream power, this will look very familiar to you in a way. So this is like a sort of advective part and a diffusive part. So a way to think about this sort of advective part, where we're advecting our probabilities that we'll find a waterfall in a particular position or a erosional front at a particular position. This is related to that deterministic part of the Langevin equation. And then we have this spread of variance, which is how the randomness is incorporated. And just to give you an idea, for a single front migrating, you can produce figures that look like this pretty straightforwardly. So this is the probability of finding our waterfall at a particular position at a particular time. And the times are shown by the colors through here. This is displacement. And our waterfall or our erosional front is migrating in the direction of the big chunky arrow. In these situations, actually, what I tend to do is start with the Dirac delta function, because we know where a waterfall is today, and we might want to understand how it evolves through time, for instance. Just to give you a comparison, the solutions to Fokker-Planck are these curves through here. This dashed line is the stationary solution. And these little circles with the uncertainties here, these are solutions to the Langevin equation, parameterized in the same way. So that's Langevin, that's Fokker-Planck. So we're advecting our erosional front upstream. It's dispersing with a probability distribution that gets lower and wider, and we can calculate a stationary solution. This comes from the other stochastic textbook, more or less. If anyone's working on stochastic theory, the Riskin textbook. And a benefit to using this is that the approach is pretty flexible, but in the end, it's probably restricted to pretty special cases. So it's pretty good probably for understanding probability distributions of these erosional fronts, these waterfalls that propagate upstream in general. But occasionally, erosional fronts are permitted to move downstream. So like this trajectory through here. So each one of these is a single trajectory of a waterfall propagating. So that's probably nonsense, really. It's very hard to think of any physical situation where a waterfall might propagate downstream in any sort of meaningful way. So we need to do something else, probably. So one way I thought about addressing this is to try and go back to first principles and develop a stochastic theory of landscape evolution from there. And that brought me to trying to think about, well, what's the simplest possible model, physical model, simplest possible model of physical erosion that I could think of? And basically it's this, which I apologize if this is a bit unnecessary for people. But anyway, it's that a threshold for erosion is exceeded. And I think that can apply to lots of different scenarios. I think it applies to this block toppling one very clearly. So in this case, in a simple schematic for how this scheme may work, this situation might work, we might have our column of rock. So like here's obviously a photo of a column of rock and a person for scale. That's sitting on some surface. It might have some water around it, so there's some buoyancy. There's another body force, all related to gravity, of course. There's a kind of torque arm, depending on the height of the column. There's a drag form, so if water hits this on the side, it's going to push, and there's a shear stress across the top. And you can calculate quite simply for different velocities of water flow, making some assumptions about whether it stays as a jet or not, whether these columns of rock are going to be stable, so they're not eroding, or unstable, so they do erode. And in a very simplistic way, this is how I kind of think of it. So for a longitudinal profile, we might have elevation as a function of distance and all these different columns of rock. And essentially what we're saying is there's got to be some relief here, some change in elevation locally that has to exceed some critical threshold for erosion to occur. So, or we might be able to say, well, instead of delta Z, let's have a change in discharge. It doesn't really matter. It's just some value has to be larger than some other value for erosion to occur. And that's the kind of jumping off point to develop the rest of the stochastic theory I'll mostly be talking about. It can be generalized. So this is that generalizing where we might have some driving force. So, it might be related to the discharge of water. There's some critical threshold we have to come over, and we reduce elevation by some amount delta Z. So these columns here, of course, I'm not envisaging there's like empty space between them. It's really just shown here like this just for visualization purposes, just to make visualization a bit simpler. So if you take that and you reformulate it slightly into this sort of algorithmic form, what you end up saying for a very simple version of this model, that the elevation at some time in the future, at some position along the river, is its current elevation if our forces don't exceed a critical threshold, or they reduce by some amount if we do exceed some critical threshold. I mean, I'm sure this is kind of fairly obvious, so do bear with me. This has some nice consequences to treating erosion in this very simplistic way. In a very simplistic way, if you just chase that through algorithmically, you can end up with simple situations that look like this. So this is elevation as a function of distance. All of these little white columns are meant to represent an elevation along a river. The gray you can regard as like air, for instance, and maybe there's a water interface. This is the starting condition, so time equals 0, and this is the critical threshold we've got to overcome. If we step on a couple of time steps, we might reduce the elevation in this way. So I'm keeping the old bits of the river so you can see them. Of course, they'd be eroded and they'd disappear. Move on a few time steps, we get this. So the different colors here represent the river at different times. If we go on to 20 time steps, we get something that looks like this. So getting things that look like big kind of shocks forming. So these might be where our waterfalls form. However, if we zoom out by an order of magnitude, so this little panel here is this panel here, we get things that are kind of beginning just to resemble kinematic waves propagating upstream. So kind of, in this case, a very simple slope propagating upstream. We zoom up by about a factor of 3 again, you really see that very strongly. So these are like stream power, basically, at some big scale. Whilst having lots of local complexity, we can get this emergent simplicity. So to try and generalize that and put this into a probabilistic framework, this is what I've been doing. So I've been working to start with a very simple scheme where we treat landscape evolution as a Markovian process. And all I really mean by that is the next state depends on the state we're currently in. So it's not got a memory. It's just dependent on the current state. And the transition equations might look something like this, where our probability that we reduce elevation by delta Z, for instance, might be this. So as we go from some time to some time in the future, we have a probability P that it's eroding. And of course, if it's not eroding, it's 1 minus P, so it's static. And that's the definition of probabilities again. And you can combine that mathematics with some simple, like Chapman-Kolmogorov type calculations, which, I mean, don't worry if those terms don't mean anything. I'll try and explain them in a minute. You can quite simply calculate things like the expected displacements again at a single step and its variance. These are kind of very standard constructs, really, in this probabilistic world. And that gives you the probability that a single step will occur and we'll get erosion taking place. You can combine that with these Chapman-Kolmogorov techniques, where you're summing up, essentially, which is the key concept here, the displacement of many steps. So you can see these little arrows up here. And you can also calculate the variance analytically. So just to sum that up, you can very simply calculate, if you start by assuming that the probability of erosion is constant in all time and all space, you get very simple analytical calculations that look like this. So we have some probability of erosion, some step that'll take place, and some time scale, and we can calculate a variance very simply as well. And that you can just chase through the sums and produce figures that look like this quite straightforwardly. So probabilities of erosion, I'm setting these arbitrarily here, but let's say the probability of erosion is 1 for all time and all space. We can calculate our expected displacement, and just like that very simple deterministic model at the start, we propagate our erosional front from down here up here along the black line, and it's deterministic, right? So there's no variance. If we do other things where we reduce the probability of erosion through time, so this might be because a waterfall or an erosional front is propagating upstream through time, and the likelihood of erosion gets less and less, maybe because discharge is not enough and we're not going to topple our columns of rock or have enough force to perform some sort of elastic erosion of a piece of rock. That gives you analytical solutions that look like this. So expected values, again, are the solid lines and the variance of the dashed lines. And you can try this for lots of different distributions of different assumed probabilities of erosion. Now, more generally, I think we probably want is some way of incorporating physics more directly. So a way I've been thinking about this is incorporating the probability that driving forces exceed resisting forces. And in a more formal way, you might write it down something like this. The probability of erosion is equal to the probability that some driving force, which I'm calling delta Z here, exceeds some critical value C. Now, you can calculate the displacement of erosional fronts for these different probabilities of driving forces and critical thresholds. So just to get your eye in, the solid black here and the dashed and the dotted lines are showing you the expected value of a driving force, an arbitrary driving force of erosion and its variance. And these different colored horizontal lines here are showing you critical thresholds. So you could already see and guess from this that, all right, well, here are driving forces for erosion. The black is generally greater than the green. So we're going to have a probability of erosion that tends to be 1 or approaching 1 nearly everywhere. And that's, of course, what you see. And what we're doing is we're propagating an erosional front from here to here. And that probability of erosion decreases as we go upstream in this kind of way for these different assumed values of critical thresholds for erosion. Yeah, so it's an example for the orange one. And from this, you can, again, just by chasing the sums through, it's pretty straightforward once they're derived, is calculate the expected displacement and the variance. And this is what you get for each of those different scenarios. So for the orange one, again, you can see we've got some expected displacement. It increases almost linearly because we're eroding nearly always until we get to about a downstream distance of about 60, which in this case gives us a chronological time of about 40. And then we're basically static. The erosion front's not migrating. And you can make the critical thresholds stochastic also and chase those sums through analytically again. So you can get these perfect mathematical solutions. So to kind of sum up that first bit, fluvial erosion is a probabilistic problem. There's helpful analytical solutions for specific problems. And what I really mean by that is specific standard distributions, normal, exponential, probability of 1 of driving forces and critical thresholds. And you can calculate amazingly, I think, these expected displacements. So like where our waterfalls are going to be, and importantly, their variance or their uncertainties analytically. But generally, probably what we really want is to move beyond this to be able to incorporate arbitrary probabilities of erosion and landscape geometries. So situations where we might not necessarily have a reasonable assumption about the probabilities of the driving forces or the critical thresholds. And so from this leads on to generating these, I couldn't resist the acronym probabilistic landscape evolution modeling. I apologize. Where we could do some simple algorithmic approaches to address this problem. So just to get your eye on, this is elevation as a function of distance. And the idea here is that you're looking at a longitudinal river profile evolving. Obviously, it's very simple. It's linear. It's just a linear slope propagating upstream through time. Time is shown here. So the river starts here in the dark colors and it progresses up to the lighter colors through here in the direction indicated by the arrow. So in these subsequent figures, these circles here are always showing the analytical solutions. And the algorithmic, it's not really numerical, it's algorithmic solutions are shown by the colors here. I'm just going to zoom onto this little box. So if we start very simply, again, assuming the probability of erosion is 1, this does what I'm sure you would expect. So we're zooming in on this tiny little box here. We've got each of these columns of rock, and we're just stepping upstream through time. Each one of these numbers refers to a time step. I'm not showing them up here just to keep things a bit cleaner looking. So yeah, that does, I think, what you'd expect. Now we can weave in, and this is work that Omar was especially helpful developing. You can weave in driving forces, random driving forces that have lots of nice statistical properties. So one of them is an Ornstein-Uhlenbeck process, which is used quite a lot in mathematical finance and a variety of other bits of physics, actually, where we have some driving force. So this is our driving force for erosion. So this might be very closely related to discharge, climate, maybe not climate, actually, precipitation, that kind of thing. And you can treat this in a very simple way. So we have some initial value. That's this red term through here, which might be this value here. So this is force as a function of distance. Again, our black and our gray are our driving forces for erosion, and the gray and the colorful line here, the orange line, is the critical threshold that we have to overcome. We have some mean reversion rate, so the rate at which this curve rolls over. We have some stationary value, so some value the force ultimately gets to if you leave it alone for long enough. And if you chase all that through, again, you can get these really very nice analytical solutions for the expected values of the driving force, which is the solid gray curve through here, and its variance, which are the dashed lines through here. And this is because the Ornstein-Uhlenbeck process locally has a normal distribution. And from that, again, analytically, you can calculate the probability that erosion occurs, chasing this through. So C here is this critical threshold, which is here. And just to show you what that does, what you're looking at here is the river profile evolving. So this is elevation as a function of distance. The gray is our river profile evolving. These are our forces and our critical thresholds through time. This is the probability of erosion calculated here. And you can see it basically produces things that look kind of like longitudinal river profiles. And it works in a sensible way that the probability of erosion down here is basically dropping to 0 because our forces almost never exceed the critical threshold. So we get a step in the longitudinal profile. This circle and the horizontal line here are showing you calculated analytical solutions. And this is showing the probability distribution of the change in relief. I'm not going to talk about this actually, but I think this actually contains useful information that we can use to parameterize such models based on waterfall, known information about waterfall distributions. So a consequence of all of this, including random, stochastic, but realistic forcing, is that we get local complexity. Simplicity seems to be an emergent property in these systems. And I think it leads us on to this worrying about fuzzy, what I'm calling fuzzy rivers, kind of uncertain positions of longitudinal river profiles. So just to demonstrate that, here, just to give you an idea for a kind of reasonably well parameterized problem. So these are forces I calculated. They're just order of magnitude estimates of forces available for erosion along a river of a reasonable size. I've tried to keep it dimensionless as much as possible, but I'm trying to put real numbers in here. So what you're looking at here is the head of a river down to the mouth of a river. This is one of these Ornstein-Uhlenbeck processes again with its expected value for the driving force of erosion and its variance. There's a critical threshold for erosion shown by the red horizontal line through here. This is assumed, but probably reasonable given some of the block toppling estimates, the estimates that we have from blocks in Iceland, for example. And there's 10 trajectories of the driving forces shown here in gray, just to give you an idea of what they look like, really. The probability of erosion calculated analytically is here. So again, it kind of makes sense. Nearly always for this whole patch up here, our driving forces exceed our critical thresholds. And here they dip below. And so our probability of erosion decreases. Now, for a single realization of a river profile, so this is elevation as a function of distance, again, very similar format to before, but now our probabilities of erosion don't have to be one everywhere. I start with a very simple initial condition of a linear profile, and it propagates upstream through time. And the times are shown by these colors here. And each one of these colorful lines, each one of these gray or black lines through here is just the river at a time. They're just contours, essentially. But that's okay. If we zoom in on this patch through here, this is what the river looks like at these scales. So again, this is just the river evolving through time over this shorter time range through here. Now, this is just for one realization. If we do it again, so we rerun this whole scheme again, we can get an alternative but equally plausible river at these small scales. And it's quite different, actually. Like if we were worrying about the block toppling of an individual block here, which for Iceland might be once per year to once per decade, we could quite dramatically change how we think the river evolves by focusing on those scales alone. Now, if you zoom out, and this is for just showing you an example for 10 different runs of this scheme, this is what I mean by the kind of alternative fuzzy rivers. All of them are probably equally valid, but they, at some large scale, they show you this kinematic propagation of erosional fronts is fine. But at local scales, there's a lot of variability. So just to zoom in on this patch, this is for 10 different rivers at these scales, these smaller scales. The thickness of the lines and the colors don't mean anything. They're just shown there just to enable you to see the difference between the rivers at these different times. They're pretty different, right? So like if you were to look at an erosional history of one of the rivers at one of these scales and you get some rate from, say, exposure age dating, how do you know what's reasonable to scale up to bigger scales? I think that's very tricky without thinking about it in a stochastic framework. So just in the last minute or two, just to show you that there are quite nice comparisons between the stochastic stuff and the phenomenological approaches, stream power approaches at big scales. These are just 3 examples where we start with very simple schemes where this is just a linear starting condition. I'm only showing the colors for the first, I think this is the first 100 time steps, just so you can see them, and then the next are just grayed out. But you can see the long profiles at those separate times by the light gray colors. And the zooms are shown by these little dashes here and here. The eagle-eyed will see that these aren't monotonic functions. So we don't have quite the same challenge that we have with stream power. Like we don't require sink filling. We don't require monotonicity. That this all just comes out in the wash with a stochastic framework. If you compare that to a stream power erosion model here, we played with this a little bit, and I know others have, just adding in arbitrary noise, essentially. You can get things that look like this. So just to show you an example here, this is the block topple, I'm calling it here, really the stochastic approach, and then the stream power approach at these big scales. And they're basically comparable, which is fine. Stream power, again, these are numerical solutions to the stream power models. So they have this kind of arbitrary, artificial viscosity, essentially, that comes in to stabilize the scheme. So that's the cause of that drag down here. That's the cause of the mismatch down here. So to conclude, I think there's quite a lot of mileage actually in bringing stochastic theory to landscape evolution in the ways that I've been talking about. I think there's more work to be done on this, but I think it helps to quantify the limits to what we can determine or extrapolate from observations. It's got some really nice properties, I think, mathematically. There's no sort of mathematical fudging. So lots of us who've worked on stream power modeling will know things like when you have an exponent on the slope, you begin to have to talk about things like shock waves, which are really difficult to deal with numerically, and I think really difficult to deal with in continuum mathematics actually generally. None of that arises when you deal with landscape evolution in this kind of stochastic way. You can build it from first principles, so it means that you can relate it to the physics of erosion and the driving forces, which I think is helpful. And I think, I mean, I'm not sure because we've not done millions and millions of tests, but I think it's pretty unavoidable that you can have systems that are locally complex and also have emergent simplicity. I think it's true to say that exists within a self-consistent theory. So there's a whole pile of next steps. I mean, this is early days, right? So an obvious thing is, well, can we do better to determine critical thresholds and forces? And this is part of the things that I was in Caltech talking to Mike and co. We need to be able to demonstrate that this approach, much like stream power, it's so successful because it can reproduce lots of observations, certainly at big scales. I think this needs to be demonstrated for this kind of stochastic theory. Obviously, something that could be done is I think it's actually quite challenging, but generalizing to 2 dimensions has lots of obvious uses. And in the end, I think it probably, we want to make it invertible for interesting things like uplift rate histories. So I've kind of gone very quickly over stuff, derivations and so on are in this paper from me and Omar. And I know this is being recorded, so I'll leave the select references up here. I know I've not really talked about papers from various people. I should say that the vast majority of very excellent work done on this stuff as far as I'm concerned, in our community, as far as I'm aware in our community, is people working on bedload transport and sediment transport. So Christoph Ansi's paper in particular was very useful. There's a whole load of other very good papers, Furbish, Parker, Effie Fufu, Giorgio, people like that have done lots of good stuff on sedimentary stuff for sure. Okay, so I'll leave it there. I'm gonna have to finish this so I can see people.
Thank you, Rob. Thank you, Gareth. Thank you. So let's see. The chat is open for everyone to ask the question. I'm going to also modify the view since I'm recording here. But we'll just leave you the possibility of sharing. You might as well actually keep your slides on. Maybe it might be able to answer some of the questions.
I can't see anyone when I do that. So you might have to
right. All right.
Let me do this and then I can see people.
Yeah, let's do that. Let's do that. I might start with a question that probably reflects my anchoring into the physical reality, trying to elevate to what you were doing here. I think I understand so your threshold is really inspired by that block toppling examples that you clearly showed at the beginning from Iceland. At the end, you talked also about the work that was done in bedload transport and these sorts of questions where we also have a threshold. But often what happens is once we are past the threshold, we move whatever is in excess of that threshold. And I was surprised, and maybe there's nothing to be learned out of my question. It might just be reflecting my confusion. You showed us that once your delta Z is greater than C, your threshold, then what you remove is delta Z itself. But not the difference between not delta Z minus C.
Yes.
And I was wondering, would that change anything in the behavior? Would that be exactly the same thing, just changing the pace, or is it a daft question?
No, I don't think it is. I worried about this a little bit. So the reason why I went for that approach at the start is just because it's simple, because everything's contained within the geometry. So the delta Z being the relief, the change in relief locally. But I think that that's not, it doesn't have to be that. Like, that this business here, let me, I'll do that. If I do that, I'll do that. Yeah, this business through here. Like,
Okay.
it doesn't have to be delta Z in this way. It could be, little delta Z. And there's some
Okay.
other amount removed. And I think, this obviously comes down to very much the physics of the particular problem that you're working on. But I think in a way, the crucial thing is that there just is some critical. I think it's really hard to think of an erosional model where there just isn't a critical threshold you have to overcome.
Yeah.
So this is a very, I don't know what you'd call it, basic or sort of stylized example, but some grounding in reality, I think. But I think you could apply it. I've done this in a couple of, well, in one other paper. You could try and apply this to things like impacts. So like the elastic, having to overcome the elastic strength of a substrate. So like is it the biota stuff? Like classic impact studies. It's essentially the same kind of thing. Like you've got some maybe velocity you have to overcome and some elastic strength you have to overcome for erosion to occur.
Okay. Right. So this removal of the entire big delta Z is not, it's not necessarily it's one of the options amongst many ways that you
Yeah.
could transmit this erosion information.
Yeah.
Right.
Yeah. I thought you were going to ask about, well, what happens when you get rid of delta Z? Where does it go? Which is another issue.
Oh.
So
But I thought it was falling off the graph.
yeah, that's what it does. It's like it evaporates into the ether, which is obviously nonsense. So we've played with other scenarios since we did this stuff where you can take care of that. So what happens if you start to distribute the sediment essentially and some of the critical thresholds? But I think a general challenge is trying to come up with the simplest scheme you can, I think is always useful in these geomorphic problems. Like it's easy in a way to always add complexity to these problems. But what I'm after very much here at these kind of early days is like very general statements that one can make about these emergent geometries.
Right. So also to tell the audience that if you don't find a way to properly phrase your question in text, you can also just raise your hand and I can unmute you. But in the meantime, I would actually maybe follow up with another question. Except Rita, you have a question?
I have.
Go ahead. Go ahead.
First of all, thank you so much, Gareth. It was really super interesting, your talk. I must confess that totally out of scope of what I'm doing. And I do have one question, and apologies if it's too simplistic. I liked it very well, as you predict using basic conditions, as you are predicting such a long-term tendencies. I was wondering if there's any factor that is actually changing a lot those thresholds of erosion, or how can you incorporate, for instance, extreme events with very high return periods on your lines, on your prediction, on your predictors?
Yeah, that's a great question. So there's a few different ways to do it in this sort of framework. So one way, if you go to these Fokker-Planck style problems, you could broaden the distribution of the variance, which would be one way to do it. So very unusual events could feature in that. So I think it's very straightforward to do algorithmically, of course, as well. So like you could have some other distribution here where you, in this case, you make your, which term is it here? Yeah, the sigma term here, very big. So you could have like very big changes that are possible in like the driving forces, for instance. So yeah, so it comes down to how you want to play with the stochasticity in here. I think there's sort of two problems in a way. So one is doing it algorithmically is quite straightforward, but what I'm really keen on generally is can we get these analytical solutions that, that are very perfect mathematically. And for some distributions, that gets harder for sure. So I think that forces you down the road, I think, of having to use an algorithmic approach in some situations, and maybe some extreme distributions will be like that, I think. So I think it really comes down to things that are, it's a big problem, I think, in mathematical finance. Like, how do you deal with some of these extreme return distributions? So if you move away from Gaussianity, normal distributions, how you deal with it analytically gets really tricky. But I think I think for us in our community, it's something that we have to work on for sure, or be worried about for sure.
Right. So I'll just continue with the question that started with the end of your previous answer when you talked about the sediments. And I was wondering if at some point in your presentation you would then switch from the rivers to the hill slopes, and whether the similar approach can help us characterize or think about the evolution of the diffusive part of the landscape.
Yeah, so I've kind of avoided that a little bit because there's quite a bit of work. So Furbish, Röhring, I'm just looking at the back end of my paper now. So they've worked on that quite a bit, I think. So they have a paper, sediment disentrainment, a concept of local versus non-local transport on hill slopes. So I think there is a lot of the stochastic theory generally was set up for diffusive problems, right? So like a huge amount of it stems from Einstein's class, his miraculous year, one of those papers on Brownian motion. His papers, well, I know it's kind of silly to say this, but it's amazing. Like in 3 or 4 lines, he lays out what then becomes basically stochastic theory. So his view on, little particles hitting big particles, like worrying about the physics of that is like, we're never going to probably have the information to do that. So we deal with it as an ensemble. That's diffusion, basically, is what he sorted out in that way. So yeah, so there's so I feel there's quite a lot on that already exists. But I think that the fluvial erosion bit, as far as I can tell, is a bit of a gap at the moment. So yeah, so hill slopes, I think probably Furbish is the place to go, I think.
All right. Well, we are reaching the hour. I think that people will have a cup of tea and digest the information. I think I look around in the room with me. People are digesting. Thank you so much for this trip. And maybe you can put back once more the list of literature on the screen so we can end the presentation with that a bit larger. Yeah, great.
It's not comprehensive by any stretch, I should say. So the paper that I have with Omar, we've many more papers in there.
Right. So folks, that's time for a screenshot. Thank you very much, Gareth, again. I'm going to stop the recording imminently, but before that, thanking everyone for their participation, and we will see you next week. For Rita, can you just tease the presentation of next week?
Right. Next week, we have Aurélie Daravanche, which is a French investigator. She's researching salt marshes and wetland areas by using remote sensing. So it's going to be a different topic, but also of very interested. Hope to see you all there.
All right. See you all next week. Thank you.
Thanks very much. Thanks a lot.